Good morning, everyone. This is Mr. Steele. I'm coming to you from an actual morning, in case you're actually looking at the time in the bottom corner of the screen. I'm here to go through the entire limits review that we wrote for 2019, just to make sure you've got that support, particularly in light of the fact that we don't have that extra review day in class to let you just kind of work through it on your own. So I'm not going to beat around the bush. I'm going to jump right in and start to work. So let's start to look at some of these problems and talk about how they can approach them and important things to know. So the first problems from this section, I believe it's questions 1 through 9, all involve a set of 3 functions that you were given, and then every type of limit you can basically imagine is manufactured out of that. So we're going to get to see pretty much all the techniques for pure evaluation of limits in the first 9 questions. As with every one of these problems, one of the first things you have to do is you have to kind of rewrite the function, or we have to use the set of functions up at the top to really see what kind of structure we have to decide what techniques we might actually use. So on this first one, again, I think it's a pretty straightforward problem. We have what turns into being just a straight up rational limit. So we've got a polynomial over a polynomial, so it's a rational. And of course, before we do anything else, it's important to at least attempt direct substitution. And remember, our best strategy here is to draw these little arrows so we see if each one goes mutually to 0. Now in the denominator, I get 18 minus 2 times 9, which is clearly 0. In the numerator, I get 27 minus 24 minus 3, which also equals 0. So this is a trim the quills situation. We've got an indeterminate form. So it's time for us to attempt to trim the quills using one of our algebraic manipulation techniques. Looking at these guys, I'm thinking factoring. Like rational is pretty much factoring is your strategy. So as I go to attack this thing for the first time, I know the denominator is going to factor. I can pull out a GCF of negative 2 and be left with x squared minus 9. And although I'm kind of getting ahead of myself, by knowing that, I can also rewrite that denominator as negative 2 x plus 3 x minus 3. And the reason I'm doing this first, not only because it's a little easier, but because it confirms for me that yes, we're going to find an x minus 3 factor down there. That x minus 3 must be what's causing the indeterminate form. We're getting 0 over 0 because of an x minus 3. So what I'm going to do now in my numerator is as I look at this expression, I know something. I know I've got to be able to factor this into something times x minus 3. Because if it doesn't, then it will never end up going away. So this is just kind of a speculative form of factoring that I use. I basically know that I've got to have a factor of x minus 3. Because of that, I can go ahead and figure out what the other factors are just by looking at the polynomial. So the first term has to be 3x squared. If we're multiplying it times x, that means 3x is our first term in there. And our constant has to be negative 3. And in order to get it to multiply out to negative 3 times negative 3, we get a positive 1. So if you've seen me do these problems really fast, other than the L'Hopital's rule, this is one fast way I can do it. And it's a fast way you can do it too. I can't tell that you didn't factor with butts up or some other strategy. So in looking here, just to make sure, we get 3x squared minus 9x plus 1x, which is minus 8x, minus 3. So it looks like we factored perfectly, which means we've now got everything set, even if we weren't really super comfortable doing any of the factoring strategies. As we expected, the x minus 3's divide away, which gives us the limit as x approaches 3 of 3x plus 1 all over negative 2 quantity x plus 3. At this point, I notice there's nothing making this go to 0, so I can wrap this thing up just by doing direct sub. Again, I'm going to be super explicit as I go through these things while moving pretty fast though, so hopefully that's okay. There's our answer. We could box that if we wanted to, but this would probably be, shouldn't go all the way here. Numerator is 10. The denominator is negative 2 times 6. This is going to be 10 over negative 12, which is negative 5/6. And there is our limit value. So the y value we're approaching in this case is negative 5/6. Moving on to the second one, I noticed that we have a complex fraction here, which has already kind of led me to start to think that we're probably going to have to do some sort of common denominator technique. But again, we'll see what happens. Maybe something else will happen. So first, just as we did before, let's make sure that our limit looks like an actual limit and doesn't have a random g of x sitting in there. This will be 2/9 minus 2 over x plus 3. And all that will be divided by x over 10 minus 3 over 5. So doing our quick little direct substitution check first, we get 2/9 minus 2 over 6 plus 3, just 2/9. So the numerator goes to 0. Not a great start. Down here we're going to have 6 over 10 minus 3/5. Those are equivalent fractions, so that's 0 as well. So once again, we have an indeterminate form. We need to trim the quills. And by the presence of these fractions inside the numerator and denominator respectively of our rational expression, or our fraction, I'm going to assume that we need to do common denominator work. So going down here, I'm going to go ahead and start the common denominator work. So I'm going to leave a whole bunch of space here. Space, the final frontier. These are the voyages of the Star Trek Enterprise. Okay, so from here, looking at our expression, we need a common denominator. So in the denominator, this is actually really nice. 10, all we need to get both of them to have a denominator of 10 is multiplying the right fraction up and down by 2. In the numerator, no such luck. We have to multiply up and down by x plus 3 on the first one, or the left fraction. And then on the right fraction, we have to multiply up and down by 9. So lots of little pieces here. And again, if you're watching me write all these limits out and you really don't want to do that, you can watch the video in the Google Drive specifically about when to use the limit and when you have to and stuff like that. For now though, what we've created is we have our new numerator denominator, which is 9x plus 3. On top we have 2x plus 6 minus 18. I think I did that right. Let's see. Yep, looks good so far. Down below we have x minus 6, and we're over 10. So at this point, we're going to be dividing fractions. I can tell that. So I'm going to try to condense a couple of these operations. Well, you know, let's be careful. We're going to get 2x minus 12 over 9 quantity x plus 3. And then we're dividing that by x minus 6 over 10. So moving a couple pieces together kind of all at once, just to kind of bring all this together. And now that lets us continue our limit, but I'm going to go ahead and do the flipping now that would come naturally afterwards. So of course 2x minus 12 becomes 2x over 2x minus 6. So all over 9 quantity x plus 3. Then we're multiplying by the reciprocal, 10 over x minus 6. And the beauty of that is, of course, our x minus 6's divide away. Now we have trimmed the quills. We are now facing the evaluation of a limit that agrees at all but one point, that point being x equals 6, but it won't matter for us. We now have 20 over 9 quantity, x plus 3. Given that, we can perform direct substitution now. We'll have 20 over 9 times 9, which is 20 over 81. So the second problem gave us an opportunity to see the common denominatoring technique that we talked about for trimming the quills. Worked out pretty cleanly, but you notice organization was important. I wasn't trying to cramp all this work into a small space, and I did do a number of lines of work just to make sure that I was able to work my way through. Okay, this brings us next to question number 3, and I'd say question number 3 is the question that I spent the most time trying to design. I was really trying to make sure that I created something different and kind of new to get you comfortable with the techniques regardless of what they look like at first. And I think question number 3 is a good accomplishment of that. So first, putting in the function pieces that we now have, we have the numerator with the square root of h of x, and if h of x is x cubed minus 10x plus 40, which I'll admit is fairly spicy, but not as spicy as subtracting x to the 3/2 power. That is an aggressive numerator right there. Down below, we have 3x squared minus 12x. So again, pretty interesting. We'll try direct substitution at first, assuming that it is going to in fact probably need it. In here we'll have 64 minus 40 plus 40. So of course that's root 64 minus 4 to the 3/2. And as I said, root 64 is 8. 4 to the 3rd is 64. 1/2 powered is also 8, which means our numerator is in fact 0. So we have the starting position for an indeterminate form. In our denominator, we have 3 times 16 minus 12 times 4. That is 48 minus 48, which means that we also have 0 over 0. So once again, we're in that familiar zone of an indeterminate form. So in order to do this, we're going to need to attack with one of the trimming the quills techniques. And as we mentioned in class, the presence of that square root on the numerator suggests to us that we're going to probably use the rationalizing technique. We're going to try to multiply by the conjugate as we go forward. So in doing that, I'm going to, in fact, jump right into that as the technique. In my denominator, first though, I'm going to go ahead and factor out a GCF of 3x, because I notice that leaves me with a factor of x minus 4. And as always, since we're taking the limit as x goes to 4, and since we just saw that we get 0 over 0, Seeing an x minus 4 down there is good confirmation that that's what we're seeking. We're trying to find the x minus 4 that's embedded into the numerator. In our numerator, we have the square root of something kind of complicated, minus x to the 3/2. So, I mean, yep, that's as big and aggressive a numerator as we can get. And what we're going to do is we're going to multiply up and down by the conjugate. And so that numerator will have the same two ingredients it had before. So it'll have the square root of the cubic polynomial. And it will have x to the 3/2. That has not gone anywhere. What it's not going to have, though, is the minus sign. Conjugate always has the opposite sign because what we're trying to create is a difference of squares. Now from here, again, sliding through some of these pieces as quickly as I can, just because it's going to be a long haul here. The numerator is going to be x cubed minus 10x plus 40. That comes from the square root squared. And then it's going to be minus whatever x to the 3/2 power squared is equal to. And now if you think about it, x to the 3/2 power to the second power, you multiply the exponents, and you're actually just going to get x cubed. So to save ourselves a little bit of time, I'm going to do that already. Our denominator is pretty aggressive. See if I can take it. I can't. So of course I'll write it. We have 3x, x minus 4 times that conjugate factor. And again, one of the most common mistakes people make is that conjugate factor sometimes gets lost in the shuffle. Make sure it doesn't, otherwise you can't possibly get the right answer. In our numerator, we can get rid of those pieces. And so they're just completely gone. And now, looking at our ingredients here, we get to go ahead and continue forward. So from here, we've got a denominator that has a bunch of stuff. In our numerator, we have negative 10x plus 40. And that has a GCF of negative 10 that, when factored out, leaves us with that x minus 4 that we were looking for all this time. That means we're actually in position to divide out that factor, causing the indeterminate form. Like our algebraic manipulation has been fruitful. So with that in place, let me finish that square root. We can divide that out. That means our limit, which again I'm going to write one more time, just because I like really seeing that limit written once with the function that agrees everywhere except at one point. We now have a numerator of negative 10, a terrible looking fraction, now it's nice, and a denominator of 3x times that conjugate, with the square root included. So at this point, we can plug in and evaluate at x equals 4. Our numerator is negative 10. Our denominator is 3 times 4, again plugging in. And then because we already did this kind of work with the original numerator, I know that this is going to end up being the square root of 64, and this is going to be 4 to the 3/2 or 8. So bear with me for a second. We're going to get a numerator of negative 10. Our denominator is going to be 12 times 16. And now keep in mind, if you're not sure what 12 times 16 is, that's totally fine. You don't have to multiply the whole thing out. We could just box that as our answer because it's exact and correct. But of course, I see some pieces we could simplify. I'm going to factor out or divide out a 2 from the numerator and denominator. So 10 divided by 2 is not 6. And from there, it's going to leave me negative 5 over 6 times 16. And I do know 6 times 16. Don't know why I know it, but I do. It is 96. So there we go. We've gotten to our answer. And again, that was pretty crunchy. That's an aggressive problem. That's a challenging one with all sorts of math in there. If you can do that, then you should be good on any limit we have to evaluate on any test that comes up soon. Okay, that brings us to question number 4. Question number 4 is a limit as we approach infinity. So basically, before we start, I want to see what this function actually looks like, so we can maybe check by direct substitution. Looking up there, we have 5x plus 1 squared. Nothing too crazy there. The denominator, we have f of x plus 2. Well, f of x is 3x squared minus 8x minus 3. And if we do minus 3 plus 2, we're going to get minus 1. Now, because I know that, well, just kind of playing along for a second, if we did direct substitution at this point, we'd have infinity squared over infinity squared minus something, something, etc. I think you can probably believe me when I say that this thing is definitely going to infinity. So that makes this into, oh, can't write that. Apologize. We're supposed to have the fraction bar. It's going to infinity over infinity, which means it too is indeterminate, just in a slightly different way. When we go to evaluate it though, we have strategies to handle this. This is just a rational expression. So first of all, our numerator multiplies out to 25x squared plus 10x plus 1. If that was like to the 5th power, I wouldn't multiply it out. I'd kind of write things in a different way. But this is a pretty easy one, so I'll do it there. Denominator stays the same. Okay, from here, if we wanted to evaluate this, I know that you can probably already say that the answer here is 25 over 3. And as I said, in a multiple choice kind of context, most of the time I'm okay with you just doing it that way. But in this case, I'd like to make sure that we do things correctly myself. So what I'm going to do is I'm going to do things like I'm going to kind of demonstrate why it is that that sort of controlling term analysis works. I'm going to multiply up and down by 1 over x squared, which I think for 3rd and 6th periods last week we called nerfing. We're going to nerf the fastest growing term. So the analysis that led me to 1 over x squared and not something else was the fact that the numerator's highest degree was 2, so is the denominator's. So basically let's multiply by 1 over x to the highest degree in the problem, or in the function. So with that in place and distributing it all through, what we'll end up with here is a numerator of 25 plus 10 over x plus 1 over x squared. Our denominator is going to be 3 minus 8 over x minus 1 over x squared. Now when we direct sub with infinity, let's see if I just say this correctly. If we direct sub with infinity, then our numerator will be 25 plus 10 over infinity plus 1 over infinity squared, which we know is infinity. Infinity to any positive power, positive integer power is infinity. Down below we'll have 3 minus 8 over infinity minus 1 over infinity. Looking at our ingredients here, that'll be 0 for each one. That leaves us with our answer we were expecting, which was 25 over 3. So again, all depends on the context. I think it's good. I would love if you did it this way every single time. But at the same time, like we know that there's limited time, so just kind of read the context. If you're looking to show work and kind of show why it happens, really want to see that controlling term analysis work done. If not, you can speed through it a little faster. Okay, moving forward to number 5. Number 5 has a square root. We're taking the limit as x approaches negative infinity. Just to make sure we can see our problem here, I'm going to go ahead and rewrite it with the function value plugged in. So this is root 25x to the 6 plus 13. In our denominator, that's h of x, also known as x cubed minus 10x plus 40. So in this case, I'm not going to do a direct sub check in this case, although I probably should. I can see that it's going to go to the square root of positive infinity to the 6th over infinity cubed, so it should be fine. Instead, what I want to focus on is first trying to narrow this down and whittle it down to the terms that matter most. So basically, the highest degree term in the numerator is that 6th power, so the 13 doesn't grow fast enough for me. The denominator is x cubed and the other stuff, so I'm going to ignore those other ones. And so at this point, we're going to transform this limit as x approaches negative infinity to the limit of 25x to the 6th over x to the 3rd. Now at this point, methods may vary a little bit, but I'll remind you that hopefully in your head after last week, you know that the square root, or you remember that the square root of x squared is equal to the absolute value of x. And honestly, hopefully that's gotten into your head for the first time, because only Justin in class was able to say that off the top of his head. So know that. Okay, so with that in mind, we need to think about that square root as the square root of 5x cubed squared. The reason being, we can rewrite this limit as the limit as x approaches negative infinity of absolute value of 5x cubed over x cubed. So this way we're getting it to a position where we can start to do the sort of sign analysis we'll need. Now a couple little pieces here. First, the absolute value of 5 times the absolute value of x cubed. The absolute value of 5 is just 5, so I'm going to pull that out in front. And then second, because we've got absolute value of x cubed over x cubed, I'm going to rewrite this as a single limit, or as a limit of something to a power. So I'm going to rewrite this as the limit as x approaches infinity of absolute value of x over x. I'm going to make sure that whole thing is raised to the 3rd power. Now, we've got everything set up, but the problem is, of course, how do we evaluate that limit? And the way we evaluate that limit is we picture what the graph of absolute value of x over x looks like. So if you'll recall, absolute value of x over x has a jump at x equals 0. If the values are positive, they will be equal to 1. And if the value of x is negative, it will be equal to negative 1. And of course that should make sense, because in our minds we want to just divide out that x. But unfortunately, because of the absolute value, the sign changes. Top's always positive, bottom changes signs depending on where we're at. So in this case, though, because negative infinity is all the way to the left, we're on the branch right down here. And clearly the y value that's approaching is the same one that's always approaching on that side. It's negative 1, which means that our limit is 5 times negative 1 to the third power. Negative 1 to the third power is negative, which means this is really 5 times negative 1, which means that our horizontal asymptote, or here our value of the limit, is negative 5. So again, lots of ways to get there. You might be able to find a quick way to do it. I certainly did it different ways in the past, but this is a good, mathematically sound way to approach the problem. Okay, our next problem is one that looks kind of intimidating. It looks like another common denominator structured problem, but for the moment, let's just start by writing it out and seeing what happens. It's kind of the safest place to go. So we're doing the limit as x approaches negative 2. We've got f over h. We're subtracting 5 over 26, which looks, pretty strange. So it seems like it's got to be like a perfectly chosen value to make this thing go a certain way. And it's all over g. So this is what we're trying to evaluate. Now, as you jump into it, there's something that's kind of interesting that kind of pushes me in a different direction right off the bat. If we plug in negative 2 into our denominator, we get 2 over negative 2 plus 3, which is literally just 2 over 1, or 2. What that tells us is that we shouldn't have anything indeterminate in this problem. Our entire denominator is not going to 0. So unless something weird happens in the numerator, we're basically done with this problem. We just have to direct substitute and evaluate. So let's see what the numerator looks like. If we plug in negative 2, we'll have 12 plus 16 minus 3. That will be over negative 8 plus 20 plus 40, all minus 5 over 26. Simplifying some pieces up here, we get 28, 25 over, and let's see what we got. We have 60 minus 8 is 52. So we've got 25 over 52 minus 5 over 26. And if we get a common denominator by multiplying up and down by 2, we'll end up with 15 over 26. So pretty amazing, I would say. 15 over... Oh, excuse me. I lied. 15 over 52. I said that answer didn't feel right. But 15 over 52. So to bring this all together, it's going to be equal to our numerator is 15 over 52. Our denominator is 2, which makes our entire value 15 over 104. So the reason I wrote this problem this way and included it here was to remind you that you should never just quit on a problem before you get there. Like, if you're looking at a problem and you're trying to decide, is this worth my time? Am I going to be okay to do this? It looks kind of hard. At least try direct substitution. Maybe the problem isn't even really a problem at all. Maybe it's already there for you, just waiting for you to plug in. So pretty straightforward, but a good one to see every once in a while. Okay, moving forward to number 7. Number 7 features some pieces that remind me of black shirts with white dots. I'm seeing a general behavior limit right here because of the presence of the x does not equal versus the x equals. So basically this is one of those situations where there's some sort of hole that's being created by this behavior. So first and foremost, let me redefine k, so that way we can kind of work our way through. This will be 2 over x plus 3 when x does not equal 2. And then it'll be f, which is 3x squared minus 8x minus 3 when x does equal 2. Now for us to evaluate the limit as x approaches 2 of k of x, we're going to use the general behavior. And the general behavior is right up here. It's the general behavior because it's what's happening at all those values around 2, on both sides of 2 even, not just what's happening at a single point. So using the general behavior, we've got to plug 2 into 2 over x plus 3. So 2 over 2 plus 3 is equal to 2/5. So that's saying that our y value is getting closer and closer to 2/5 from both sides, even though the value at 2 is something else. Specifically, what is that? -4, -7. Like what's happening in general is right there. So this is what we call our general behavior limits. Pretty simple and straightforward to evaluate, but easy to mess up because it's so easy for our brains to say, well, x equals 2, let's put it in there. Not the case for all the reasons we discussed in class. Okay, moving on to question number 8. This is your left-hand, right-hand, one-sided limit kind of problem. We're supposed to evaluate the limit as x approaches -3 from the right side of L of x. We want the values on the right, so we want bigger x values. So bigger x values occur when x is larger than -3. So that means what we're going to get is we're going to evaluate whatever g of negative 3 is equal to. Looking up at our expressions, we're once again using that rational. So g at negative 3, oh geez, oh geez. We got 2 over 0. Uh-oh, whoa. Uncomfortable with that. Let's take a step back though. For x values greater than negative 3, we have the function. We know that L of x is equal to 2 over x plus 3. So that means although we don't know exactly what's happening over here, it's some other behavior, which we could graph out if we wanted to. But basically, once we get past negative 3, we've just got this function. This function has a vertical asymptote at negative 3, and we're interested in what's happening as we approach from the right. So doing some quick little work, if I plug in x equals 0, so I try to figure out what L of 0 is equal to, I'll get 2 over 0 plus 3 is 2/3. That means my point of context is right there. So I'm in the upper quadrant. Based on the look of this, we can see that there's a horizontal asymptote at y equals 0. So if we hug the asymptotes, we're going to get right here. And what that tells me is we approach negative 3 from the right side, we're actually going to get positive infinity. So this problem wasn't exactly what I expected. I expected to just plug in and get some value, some nice finite y value. But in fact, we actually turned out to be at an asymptote. And so we looked and saw from what direction, or in what direction we were approaching negative 3, and which direction that went, whether it was ascending without bound or descending without bound. And there we go. We got our answer. So tough question. Definitely tough. But interesting for sure. Okay, that brings us to number 9, the last one from this F, G, and H series. So it says to let P of x be this thing. Once again, we're using G, so let's just put that in there before we do anything else. G is 2 over x plus 3. Then we got 30x minus x squared. Okay, so looking at these ingredients, it says to find the coordinates of any discontinuities of P of x and to classify each discontinuity. So we're looking for holes, asymptotes, jumps. In looking here, the first thing that catches me is that 2 over x plus 3, since we were just talking about it. So there is a vertical asymptote at x equals negative 3. And remember, there might not be if x equals negative 3 was not less than 1. But since it's less than 1, we're actually okay. So we can definitely say there's a vertical asymptote at x equals negative 3. So there's one. The second one, I'll look at the other branch, and there's no built-in issues with this branch. 30x minus x squared, that's a polynomial. Polynomials are continuous everywhere. So there won't be any inherent issues with the second branch, the right branch, like there would be with the left branch. Instead, what we want to focus our attention on is we want to focus on what's happening at the boundary. So we're going to check for a potential jump. Do 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 do. So in order to do that, we need to look at the left-hand limit and the right-hand limit. So let's see. The limit as x approaches 1 from the left side of P of x will be one thing we calculate. The limit as x approaches 1 from the right side of P of x will be another thing we calculate. Looking at our ingredients here, from the left side, we're going to get 2 over 1 plus 3, which is going to be 1/2, perfectly good y value. Down below, we're going to get 30 times 1 minus 1 squared. That's 29. Now 29 and 1/2 do not equal one another. So what we've just shown is that the right-hand limit does not equal the left-hand limit. What that means is our limit doesn't exist at that point, of course, which disqualifies us from continuity, but specifically it tells us that there is, in fact, a jump at x equals 1. And with that, we have our only two possibilities. I suppose we could go through and just make sure that this actually does work out the way we expect it to. Let's see. Desmos. Nope, can't spell. Boom. Okay, so if we try to graph this thing really fast, we've got 2 over, x less than 1 is 2 over x plus 3. And when x is greater than or equal to 1, we have 30x minus x squared. So, yeah, we can see two things here. We can see there's an asymptote right there. Try to make it a little bit clearer. Make this bigger. You can see that there does appear to be an asymptote right there as we approach negative 3. And then second, we can see that the function's jumping right there as well. 129, and 120. Yeah, so there we go. So it looks like, in fact, we did have a jump. Looks like we've identified everything we need to. 2 different discontinuities on that function. Okay, question number 10 takes us out of that world, gets us into a place where we start looking for other things, kind of one-shot functions and questions. So 10 in particular asks us to find all the horizontal asymptotes of y equals this like ratio of 2 exponential functions. So let me remind you that in order to find a horizontal asymptote, what we need to calculate is both the limit as x approaches infinity of our function, and we need to check out, if it's not a rational expression, the limit as x approaches negative infinity of our function. So there's 2 limits at infinity we need to take into account to check to see if they have horizontal asymptotes. And actually we saw in class that this should produce 2 different ones, but we're ready just in case. So I'll start with the limit as x approaches infinity. So we'll have e to the x plus 100 over 5 minus 7 e to the x. With that in place, of course, if we did direct substitution, we'll do it really small, we'd get infinity over infinity. So that tells me we're going to infinity. To make sure that we can take care of this, I'm going to nerf the growth of the strongest growing term. So that's going to mean multiplying up and down by 1 over e to the x. And it's worth reminding you that e is just the number 2.718281828459045235 other numbers also. But in this case, it's just an expression that's exponential, so it's growing really fast. So base is larger than 1. When we distribute it through, we'll get 1 plus 100 over e to the x. In the denominator, we'll get 5 over e to the x minus 7. Now when we plug in infinity, we're going to end up getting 1 plus 100 over e to the infinity, and then 5 over e to the infinity minus 7. Well, we've talked about this before. E to the infinity is going to be infinity, which means 100 divided by infinity goes to 0. Ditto with 5 over e to the infinity, which means our value is 1 over negative 7, and that tells us we get one of our horizontal asymptotes. I'll label it at the very end. The second limit we have to evaluate is as we approach negative infinity, so going in the opposite direction. In this case, same exact function. Of course, that was the question. Now in here, of course, we can start with direct substitution, and if you recall from class, direct substitution worked really well with these guys when we were approaching negative infinity. Get e to the negative infinity plus 100 over 5 minus 7 e to the negative infinity. So looking at those pieces, familiar kind of structure, we'll get 1 over e to the infinity plus 100 over 5 minus 7 over e to the infinity. And so like we just said, e to the infinity is going to infinity. So basically 1 divided by infinity is 0, so is 7 divided by infinity, which means we're left with 100 over 5, which is 20. So that gives us a second end behavior asymptote, or horizontal asymptote. So we were asked about specifically the horizontal asymptotes, or the ha's. So basically to write those out, we use proper notation. Horizontal asymptote is an equation, so y equals negative 1/7 and y equals 20 are the 2 that this function has. And of course what they do is they describe the behavior of the function as x gets really, really big, really, really small. So there we go. Okay, moving on to question number 11. I personally found this to be the hardest one on the entire review. It was the one that I was closest to kind of screwing up. But we'll talk about it just the same. I think it's actually a good question. I just tricked myself when I wrote it. So we're given the function r of x equals log base 2 of, I'll write it bigger. R of x equals log base 2 of 7x minus 3, all minus 5, and then it's all divided by x, quantity x minus 5. And we're asked if r has any vertical asymptotes. If there's any vertical asymptote on this function. So of course the first place that I look for finding VAs is I'm first going to check in the denominator and ask myself, are there any x values where that denominator equals 0? Well, naturally there are 2. X equals 0 is 1, and x equals 5 is another. Here's the thing though, if we check x equals 0 and try to see what's going on, of course we need for a vertical asymptote the denominator to go to 0, but the numerator not to. But there's something worse at foot with the numerator. If we plug it in our numerator we get log base 2 of negative 3 minus 5. Unfortunately, getting the log of a negative base means that our value is outside the domain of the function. So 0 is not in r's domain. And that means that there's no VA there's no vertical asymptote at x equals 0. I mean, if 0 is in the domain, sure, we'd have one, but we don't here because it's not. So basically, there's no vertical asymptote at 0. So it's kind of scary. You might wonder then if there's something tricky going on at x equals 5. Well, if we plug that into our numerator, we get log base 2 of 35 minus 3, all minus 5. That's log base 2 of 32 minus 5. And ask yourself for a second, what power of 2 gives you 32? You're going to get 5. So when x equals 5, the numerator is equal to 0, but so is the denominator, which means that we have whole at x equals 5. So once again, there's not a vertical asymptote there. So now if you were me, you'd be very tempted, or me when I was doing this the first time, you'd be very tempted to just say, okay, well, there's no vertical asymptote then. But there's one thing left here that you could easily forget. So remember what the graph of log base b of x looks like, assuming, of course, b is greater than 1. So picturing that graph for a second, you hopefully recall that what it starts with is a vertical asymptote at x equals 0. After that, it's basically the exponential form, but obviously it's an inverse, so it's been shifted. Look up at our log. Basically, if we have log base 2 of 7x minus 3 involved in this function, that implies that there should be a vertical asymptote at whatever makes 7x minus 3 equals 0. That means we should expect a vertical asymptote at x equals 3/7. And x equals 3/7 isn't in the domain of the log function, but it's definitely in the domain of everything else. So we should expect the limit as x approaches 3/7 from the right side. Let's see, yeah, from the right side, to be equal to negative infinity. A quick little check here to make sure it's true. Again, using Desmos to kind of confirm the things that we're looking at. First, we'll go x, quantity x minus 5. In our numerator, I have to use change of base, by the way, to do this. If you're wondering why I'm not putting in log base 2, that's not a thing. Okay, so pretty funky looking function here. So we can see, did I put that in correctly? Log of 7x minus 3. Oh, I put minus 6, I apologize. That's why it looked weird. There we go. I was going to say it didn't look like the graph. Okay, so first of all, right over here, we are in fact getting closer and closer to x equals 3/7. Look at that. That definitely looks like a reasonable asymptote. And then second, we're supposed to have a hole at x equals 5. Let's see. 5 comma undefined. And then of course nothing at 0 because the function just kind of stops getting over there. Stays true to itself right there. So once again, we've done it correctly, but again, very tempting to forget some information about how the log functions behave. So obviously I'd consider this a really strong, like, plus kind of question. But if you can reason your way through, you're ready for the real stuff. Okay, next that brings us to 12. And I'll probably take a short break after doing this, just for a few minutes, because I'm feeling really sick to my stomach for some reason. So for number 12, find the values of m and b such that f of x is continuous for this massive function. Well, if you'll recall, the strategy that we took when working with these kinds of multi-front expressions was we basically looked and isolated the second step in the definition of continuity. We want to make sure the left-hand and right-hand limits are equivalent to one another on each side, of the boundary. So in our case, as I look, I see two boundaries, 2 and 5. So I'm going to focus on answering the question, is this function continuous at the left boundary, x equals 2? And then next, I'm going to focus on answering the same question, but at the right boundary, x equals 5. So looking at our ingredients here, we're going to do the limit as x approaches 2 from the left side of, we called this function f of x. And we want that to be equal to the limit as x approaches 2 from the right side of f of x. But we're not sure for the moment, so I'm going to put a little question mark there. We'll see what happens. Now, we're plugging in 2 though on both sides, so I can plug it into both expressions. We'll have m times 2 squared plus 3 times 2. And then that'll be equal to 7 times 2 plus b. Looking at our ingredients here, that's going to be 4m plus 6 is equal to 14 plus b. And if I want to kind of bring all this stuff together, I can subtract b and subtract 6. And I'll get 4m minus b is equal to 8. So there's a nice equation for us to work with. It's a good start for everything. Next, we can start attacking continuity at x equals 5. We're going to begin with the exact same investigation. This time, though, we want to know, does the limit from the left side of f of x at x equals 5 equal the limit as x approaches 5 from the right side of f of x? So once again, open question for now, so we include the question mark. From here, we plug in 5 to both sides, keeping in mind that now we're using the bottom two functions because we're focusing on the boundary 5. So on the left side, we'll get 7 times 5 plus b. On the right side, we'll get m times the square root of 5 plus 95, all plus 9. Pulling up ingredients here, that's going to be 35 plus b. On the right side, that's root 100 times m, which makes it 10m plus 9. And again, moving some pieces together and kind of reconciling things, we're going to get 26 equals 10m minus b. Let me make sure that's right. Yes, right. Yeah. Okay, cool. So there's our second equation. So now we've run into this situation in class. Basically what happens is we've created a 2x2 system here. We have two equations with two unknowns, m and b. They're the things that we want. So we set up a system of equations. And I'll just rewrite the order of pieces here already. So as we jump in and start to attack, I'm going to choose to multiply the first equation by -1 to get the signs to line up properly. That's going to give me -4m plus b equals -8. Down below, we'll still have 10m minus b equals 26. So as far as pieces here, that'll be 6m plus no b's is equal to 18. So m equals 3. Worked out pretty clean. Now remember, of course, once we find m, we now just need to go back into whichever equation we want. I'll use this time 10m minus b equals 26, just for variety. This will be 10 times 3 minus b equals 26. So we want to know what you subtract from 30 to get 26. I think it's pretty clear at this point that b is equal to 4. So allegedly, if b equals 4, our function should work perfectly and be nice and smooth and continuous. For the moment, I've been using Desmos to kind of make sure these things work. So let's go try it real fast. Try to keep it as visible as possible here. So mx squared plus 3x. We're going to have 7x plus b. And we're going to have m square root x plus 9. Okay, so I didn't do a good job of making that right. Greater than or equal to 5. We're going to have 2 less than x less than 5. And then we got x less than or equal to 2. Okay, so let's try these both. Okay, so as of right now, here's our function. Doesn't show a whole lot. Yeah, that's not continuous. That's just not it. We said we wanted, I think it was it m was 3? Okay, and we wanted b to be 4. And look at that. I mean, it isn't the perfect thing in the world, but clearly continuous everywhere. So it looks like we accomplished what we wanted. There it is. Remember, this one's really important. It's about organization. Like, make sure you organize things, make sure you communicate what you're doing using the second step of that definition of continuity, since the first step is almost trivial here. If you get a system of equations, resolve it using elimination or substitution, or I guess you could graph it if you really wanted to, but that's kind of awkward. But everything works from there. Next, that brings us to question number 13, which kind of mimics the structure that I like to do for kind of free response style questions, kind of that AP style. Here's some information, or here's a function, or a graph, or a table, and then draw some conclusions out of it and do all sorts of different problems with it. So in this case, we're given a table that has values for continuous functions f and g, so two different continuous functions, so we're going to have to make sure to read the correct one. We're supposed to use that to answer the questions. So the first question asks us, how many zeros are guaranteed for g on -2 to 10, and to explain our reasoning. Before we even start looking over there, since g is continuous, it's important to establish this. Since g is given as a continuous function, the IVT, or intermediate value theorem, can be applied, meaning that if we have appropriately spaced endpoints, we can guarantee particular y values and corresponding x values for each section. So now to kind of help us here, let's go ahead and I'm going to grab the table. There we go. Grab the table. We don't have to care at all about f of x right now. We will later. So we're interested in how many zeros are guaranteed. So let's look at, for instance, the first interval from -2 to 1. So in looking at this, what I can see is g of -2 is equal to -1, which is less than or equal to 0, and that's less than or equal to 3, which we can see from the table is g of 1. That means we have 1, 0 guaranteed. There is a value c between -2 and 1 for which g of c equals 0. On the next interval, there's not. 3 to 4, if we're moving from 3 to 4, we don't guarantee there's a 0 in there. Of course there could be, but we're not guaranteed one, and so we don't get anything out of there. But on the last interval, from 5 to 10, we can see that g of 10, being -2, is less than or equal to 0, which is less than or equal to g of 5. So basically we have two values guaranteed. So 2 zeros are guaranteed for this function on, -2 to 10. And as far as our reasoning, we could use the intermediate value theorem. We could also use the fact that this work is here. Like, I'd love to write a little bit more. You can read the written solutions for further. Well, okay, I'm sitting here. Why not? I might as well do everything on this. So there are 2 zeros on here because, so our reasoning here is because g is continuous and 0 falls between. We had, I think it was g of -2 and g of 1, as well as g of 10 and g of 5. So basically there's one such explanation that could be there. There's lots of different ways to state this. The nice thing is to remember, though, here, the important thing is that, yes, we're using the intermediate value theorem to guarantee certain y values that are between have corresponding x values, but in addition, we're also just saying the minimum. Like, we're saying how many are guaranteed, not how many are there, because, of course, there could be a whole lot more. We just know there can't be less, because the IVT guarantees at least one for each interval that satisfies that. So just keep that in mind. Part A, not my favorite application of the intermediate value theorem, but, you know, still a good one, a good kind of pre-Cali version. For part B, we are told it is known that x plus f of x is less than or equal to h, whatever the function h is, which is less than or equal to g of x minus 2. And this is for all x in the interval from 4 to 6. We're supposed to evaluate this? Well, when I see that triplicate inequality here, that makes me think of the squeeze theorem. So this must be a squeeze theorem question. And we were able to squeeze this in our class, so we were able to see it a little bit. So for the squeeze theorem, recall what that says is we start with the inequality that we had. They're telling us this holds for these continuous functions, at least in the closed interval, or the open interval, excuse me, from 4 to 6. So now we're interested in the limit as x approaches 5. So what we can do is we can imagine writing an inequality with their general behaviors. We'll have the limit as x approaches 6 of x plus f of x. That'll be less than or equal to the limit as x approaches 6 of h of x, that thing that we're looking for. We're trying to find the value. That's going to be less than or equal to the limit as x approaches 6 of g of x minus 2. Now at this point, 2 of these limits we can evaluate, so I'm going to go ahead and do that. I'm not going to write the full inequality, I'm just going to do their calculations. So this will be 6 plus f of 6. And by the way, the reason I can calculate this limit using f of 6 is because the functions are continuous. And recall, if a function is continuous, f of c must equal the limit as x approaches c of f of x. Really small little nuance, but definitely something that's kind of rich there to really make clear why we can do this. So 6 plus f of 6, that's going to be equal to 6 plus f of 6. We don't actually have, oh, it's f of 5, isn't it? This is the problem with wearing fake glasses, to do this so it doesn't reflect. Makes so much more sense. Okay, my apologies. 5, 5, 5, 5 plus f of 5. That's going to be equal to 5 plus -3, which equals 2. On the other side, using the same rationale, g is continuous, so g of 5 equals the limit as x approaches 5. We'll get g of 5 minus 2. That's going to be equal to 4 minus 2, which is 2. So, very interesting. What we've just shown is that 2 is less than or equal to the limit as x approaches 5 of h of x, and that limit is then also correspondingly less than or equal to 2. So now, if the limit is between 2 and 2, the only possible value, and the value guaranteed by the squeeze theorem, is that the limit will hold the same value. That means the limit as x approaches 5 of h of x is equal to 2. And if you want to say by the squeeze theorem, you can, but you don't have to. You've established all the conditions up above to invoke it, so you're covered. And so there is the squeeze theorem in action. Not particularly difficult, just a matter of writing the limit of the inequality of limits, and then evaluating everything and making sure it's sandwiched in between. As a heads up, let's say we had done this and we got that this was the lower limit was, or the left limit was 2 and the right one, no, I shouldn't use left and right. The smaller limit was 2 and the bigger limit was 12. If that was true, we wouldn't be able to conclude anything here because we just don't have enough information. Knowing the limit falls somewhere in the middle does not actually answer the question for us. The squeeze theorem requires us to specifically have the same value for both the smaller function's limit and the bigger function's limit at that point of interest. So keep that in mind. Next, we're going to look at question C. Now, as a heads up, some of you got printed versions of this that had -1 here instead of a -12. Keep in mind that those are an error. I printed the wrong copy before we copied it. So it should say -12, so you might make that adjustment now before you attack this problem, or if you're getting stuck on it, that would be why. If it was -1 instead, this function would not be continuous at all and it would blow up in your face. So it should be -12. With that said though, once we've got it corrected, we're in great position to actually do this problem properly. So we're going to do a formal proof of this function is continuous. That requires us to demonstrate 3 properties hold for the function in question at the x value in question. First one is to show that f of c exists, which in our case means we need to show p of 1 exists. So we can calculate that by finding the branch that includes 1. In our particular case, that's going to mean that we're using 2 to the 1 plus the square root of 1, also known as 2 plus 1, or 3. And I'm pretty sure 3 exists, so property 1 holds. Property 2 is to make sure that the limit as x approaches 1 of p of x exists. In order to do that, we're going to need to do the left-hand and right-hand limits. So we'll do the limit as x approaches 1 from the left side of p of x and figure out its value, and then we'll compare that with the limit as x approaches 1 from the right side of p of x. So of course we need to identify the correct branch to use. Smaller values will be the left-hand limit, larger ones will be the right-hand limit. So the smaller ones come from 2 to the 1 plus root 1, which we said earlier was 3. With our updated second branch here, we get 5g of 1. Recall, of course, that we can use g of 1 because g is continuous, so the limit and that are equivalent to one another. So 5g of 1 minus 12. Well, up there it says g of 1 is 3, so that means 5 times 3 minus 12, which is 15 minus 12, or 3. So in this case, what we just showed was left-hand limit equals right-hand limit equals 3 at specifically x equals 1. And what that tells us is that our limit as x approaches 1 of p of x is equal to 3 as well. And 3 exists, so we're good to go. Keep in mind too, is just kind of a quick little aside, this is the part of a continuity proof that you might see on an exam or the AP exam that would kind of garner the most points. So make sure you really are communicating things correctly. Notice I used proper notation, formal notation at least once before switching to the more colloquial LHL and RHL. Try to make sure you communicate everything really well as you go forward, or else you might lose points just for your presentation of the mathematics. So as far as our finishing part, remember our goal was to show that eventually p of 1 equals the limit as x approaches 1 of p of x. Well, that's true because our two values are 3 and 3, and 3 equals 3. So the third step holds as well. So we are done with the proof part. All we need to do is communicate what it was that we were doing. We've just proven, so we can say therefore p of x is continuous at x equals 3. Or at x equals 1, excuse me. 3 is the y value it's continuous at. So there we go. And we talked about it. You can write QED if you'd like to. Quote erit demonstratum. That which has been proven. We're done. That's our bat flip at the end of the proof. So again, full continuity proof. This is a really good model for the sorts of continuity proofs you might need to do. It's not trivial to just evaluate that limit. You actually had to check from both sides and communicate things like the two limits being equal gives us the limit, that kind of good stuff. So a really rich problem, really good example to look at. Okay, part D, 13D. Is there a value c for 5 less than or equal to c less than or equal to 10 such that f of x equals -1? We're to explain our reasoning. So because we're talking about trying to find a value c, this makes me think one of the value theorems, which in this case we only know one so far, so it's probably the IVT. So we're thinking about sticking some Snapple into a plastic bag and putting it right into the bloodstream, because this is an IVT time. So from here, is there a value? Well, there are a couple things that we require to use the IVT. First, we require continuity. The function has to be continuous or we can't apply the IVT. Second, we have to have boundedness, or betweenness, excuse me, boundedness comes later. Betweenness. In other words, we need to make sure that the value we're interested in is in between the two y values, or the two endpoints. So in order to do this, the first thing we can say is we're talking about f of x. So f is continuous. And the reason for that is it was given. So that's kind of our first thing. We do have the continuity that we're looking for. For betweenness, we need to calculate our endpoints. So we need to figure out what f of 5 is and what f of 10 is. Thankfully, our table gives us those values. F of 5 is -3. F of 10 is 8. So in our minds, we can see that -3 is between, or -1 is between -3 and 8. So we also have betweenness. All that's left at this point is to narrate the full invocation of the intermediate value theorem. So in this case, I'll say it this way. Since f is continuous, and we don't have to specify the interval here because it's continuous everywhere. So they say it has to be continuous on any given closed interval. So since f is continuous and f of 5 is less than or equal to -1 is less than or equal to f of 10, thereby establishing the betweenness of that value we're looking for, -1, and the two y values of the endpoints. We can then say, by the intermediate value theorem, and I'll write it out one time because I've been shorthanding it so far, by the intermediate value theorem, we now know f of c equals -1 for some c in that interval, which was from 5 to 10. And there is that beautiful intermediate value theorem kind of narrated proof or explanation there. That's just a perfect form. You can treat that as almost a sentence frame. This is what you're going to follow to show that a particular value exists. So there it is, really good, strong, representative intermediate value theorem question phrased in the way that I've seen the AP exam do in the last few years. So there is 13D. Okay, jumping on to the back side of our assignment, we're going to look at a couple other questions. Some of these have taken off old versions of exams, and I just thought they were good questions that didn't quite fit on anymore. And some of these were just kind of questions created freshly for what we have here. So the first one, question number 14, as you looked at, it tells you that you're looking at the values from a function f, and it says that there are two discontinuities on f, just so there's no ambiguity. There's a discontinuity at 2, and there's a discontinuity at 6, respectively. So we want us to, the problem asks us then to use the table to classify each of those discontinuities with some explanation. So let's start at x equals 2. So we're looking at what's happening here. So I can see those are all the values that are kind of around it. What I notice in this region is that f of 2 is equal to 42. But as I get x values closer and closer to x equals 2, my y values seem to be getting closer and closer to 4. So basically we have a situation like this. I'll just kind of narrate it down here. Since f of 2 equals 42, but the limit as x approaches 2, and I'll just go ahead and say it equals 4, but even though we know it could be somewhere just really close to 4, since f of 2 equals 42, but limit as x approaches 2 of f of x equals 4, that means that the limit exists, but the point isn't in the right spot. That means we have a hole. And actually we go play Nintendo games on that. F has a hole at x equals 2. So we're going to say hole for this case. I'm going to fill up the whole blank with that. So keep in mind again what's being really said here is we're saying that the general behavior is indicating that we're getting closer and closer to 4 at x equals 2, but yet it says the y value is up here at 42. So it's just a single point that's been removed, making this a removable discontinuity, and of which there is only one, what we call the whole. For the second one, for x equals 6, looking over on that last piece over here, what I'm seeing is it looks like on the left side, everything's going closer and closer to 8. On the right side, though, it looks like we're going closer and closer to -2. So basically, my thought here is that we have a jump at x equals 6. My rationale would be that this is true because the limit as x approaches 6 from the left of f of x equals 8, but the limit, I gotta write this on another line, but limit as x approaches 6 from the right side of f of x equals -2. So basically when the left hand and right hand limits don't equal one another, what that's telling us is that we should have a jump. And in fact, that is what we have in this particular case. So I'm really a big fan of this question. I thought this was a really clever one, put together a couple years ago, simply because it gives you a whole bunch of values and you have to kind of interpret it or sketch your own picture. But again, it's just kind of a nice way to look at things numerically and still be able to determine some really important analysis for a function. Okay, for 15, it says, explain why the statement below is false. If p of x is a polynomial, then the function given by f of x equals p of x over x minus 5 has a vertical asymptote at 5. So now, before we dig too deeply into this, let me point out first that a lot of people fall into this trap. When I used to ask this as a true or false question, they fall into this trap because they go, well, x minus 5 is in the denominator. Of course there's going to be a vertical asymptote at 5. But unfortunately there's not. There are values of p that make this absolutely not a vertical asymptote there. So what I'm going to do is I'm going to let p of x be a multiple of x minus 5. Maybe I'm going to let p of x be 10x minus 50, which is just a fancy way, a simpler way of writing 10 quantity x minus 5. So, and again, this would be a good way to narrate it. This would mean then that f of x equals 10x minus 5 over x minus 5. And if that's true, we can see that what's really happening here is we're creating not a vertical asymptote, but a hole. So basically we'd say then f of x has a hole at x equals 5, not a vertical asymptote. So again, we've seen this idea come up multiple times in multiple different ways. For the moment, just want to play along. But basically you could list any multiple of x minus 5. You could just say if p is a multiple of x minus 5 that this happens, but if I were grading this, I would need to see some mention of the fact that you might have a hole there, and I'd need to see some sort of reason why, be it a counterexample or some sort of explanation about what counterexamples would look like. So again, really nice question, one that I think you understand conceptually, but sometimes people get thrown off by these sort of true-false questions. But you can probably bet that this will be on a standard quiz, if not your exam also, at some point this term. Okay, for number 16, the statement, if the limit as x approaches -2 of g of x is 15, then g of -2 equals 15 is false. So they're once again telling us the statement is false. Our task is to explain how this statement could be true. So we're thinking, when is it that the limit as x approaches -2 of g of x has to equal g of -2? So that's what we are trying to ask. And the answer is a particular type of function, or if the function g has a particular property. Specifically, this is the third property that's required for a continuous function at a point x equals -2. So basically what we can say is if g of x is continuous, and basically it's not even enough to just say if g of x is continuous really, although I'd forgive you if you did. If g of x is continuous specifically at x equals -2, since we don't care what happens elsewhere, we're just interested in this neighborhood, then the limit as x approaches -2 of g of x is equal to g of -2. So basically that's what we require. And if I were grading this, that's the phrase I'd be looking for. If g is continuous, Technically, we should probably also make note of the fact that g of negative 2 would also have to be equal to 15, or else that statement would be false. But for the moment, we'll set that part aside. Okay, finally, we're reaching into question 17. 17, the last one here. 17 is the final question, but of course it has 96 parts. Thanks, writer. Oh, that's me. Okay, so jumping into this last one, it says the graph below, or in our case at right, shows the piecewise linear function g of x. We want to use the graph to answer the questions that are below, or to evaluate the limits in our case. So I'm going to go through these pretty quickly. I think they're pretty self-explanatory applications of limits, like they're pretty visual, but a couple of them are really tough, so we'll talk about those guys when we get there. Okay, so first we want the limit as x approaches negative 2 from the left side, if I'm reading that correctly. So negative 2 from the left side. Yes, it's approaching a hole, but we can see that the y value that it is approaching is positive 3. So this is equal to positive 3. For 2, the limit as x approaches negative 2 from the right side of g. So looking over at our picture, as we approach negative 2 from the right, we're approaching the x-axis, which means y equals 0. And note that the right-hand limit does equal the value of the function right at that point. Okay, for question 3, you might think it was asking about the limit as x approaches negative 2, and it does not. So just note the limit as x approaches negative 2 of g of x based on this information does not exist, well, because of those two pieces of information. Down here, though, we're interested in the limit as x approaches 2. So looking over at our graph, I can see that from the left and the right side, even though the function value is not there, the limit is clearly still approaching y equals 2. There's just a hole at that point where the point has been removed. So basically here, I can say that my limit is equal to 2. Okay, moving forward, it does ask us for g of 2 next. G of 2 is the literal y value. Looking at our picture, that's going to be equal to y equals 4. Next, we have probably the most challenging question in this last page. It asks us the limit as x approaches negative 3 from the right side. So looking at our picture, or trying direct substitution here, I can see that g of negative 3 is equal to 0. So in a sense, it's very tempting to just say, well, this equals 1 over 0, and it does not exist. Unfortunately, because this is a one-sided limit, it's not a good idea for us to just settle for simply saying it does not exist. We want to be more specific. So in order to do that, we need to think about what's actually happening here. And there's a couple different ways you can do this. So bear with me on a couple different approaches. The first thing that I want to do and think about is just kind of take a look at what that looks like. So as we go through here, we're basically trying to decide between whether or not this limit is positive or negative infinity, because we know this leads us towards one of those two infinities. So in this case, for x values that are less than negative 3, and actually technically we got to say that it's, here, let's say this correctly. So for our section of the graph we're interested in, for x values that are between negative 3 and negative 2, can you agree with me that g of x is positive? Like looking at the graph, do you agree that this chunk is above the x-axis?
Yes, we do.
Exactly. That chunk of the graph is positive. What that means then is we can't approach a negative number when we take its reciprocal. That means the reciprocal, 1 over g of x, also has to be greater than 0. And that should make sense, like that's literally true. And the thing is, if that's true, then we need to describe 1 over 0 in this particular limit as being greater than 0. And that means that the only possible way that we can have this happen is if this limit is equal to positive infinity. And in fact, that is our limit. So that is kind of option number 1 for an approach to take in this issue, in this problem. A second approach to take would be to literally find the equation of g of x. So looking at g of x over in this chunk of the graph, if we look, we can see that there is a line segment there. So we could talk about what g of x's equation is for x values less than negative 2. So looking at the equations that we have, I'm going to say that the line is y minus 0 equals 3 for the slope, because it's going up 3 over 1, quantity x minus 3. That means that our equation is y equals 3x minus 9. So for us, that means we're trying to evaluate the limit as x approaches negative 3 from the right side of 1 over 3x minus 9. And if we picture that function, or try to kind of sketch it out, we're going to have a vertical asymptote at x equals negative 3. And then from here to decide what the values are, like where we're actually looking, we want values that are larger than -3. So did I mess this up? I feel like I've got it so far. We'll find out. Did I do that correctly? Okay, I think we're okay. At x equals, oh, that's why. It's at, that's supposed to be, I think I screwed up the equation here, didn't I? This is supposed to be x plus 3. Yep, this all makes sense now. Okay, good. That becomes x plus 3, this becomes 3x plus 9, and this is 1 over 3x plus 9. There we go. Now when we plug in a point to check for where those regions are, if we plug in, say, 0, we're going to get 1 over 9, which means that our graph looks like this. If we want to see what the limit's doing there, we can see that the limit's going up, which leads us to an answer of positive infinity. There we go. Sorry for that mix-up. That was my mistake. I had the sign mistake happen, which has happened a lot in this unit for me on the problem set solutions, but there's everything that we need. And again, this is hard. This is a hard problem. This is the diamond of these problems. This was tough. So there we go. Okay, so moving down to 6, we're supposed to evaluate the limit as x approaches infinity. And in a sense, this second option we just did here actually provides a really good model for what to do. So as we're going to infinity, those are going to be big x values. So I'm interested in what g of x is doing when x is greater than, let's go with 3. So we know that there's a line over here, looking at the graph over in this region. So looking at the graph here, if I kind of plug in the values, we'll have y minus 4 equals, let's see, we got to go up 1, 2, 3, 4, 5, 6, 7, 8, and over 2. So the slope is 8 over 2, or 4. And so you can kind of see I'm using as my point of context this point over here. Lots of different ways to write the equation of a line, by the way. Your call which one you want to use. So with that one over there, that's at x equals 5. So from here, that means our equation is going to be 4x minus 20 plus 4, which is minus 16. And that basically adds up. We should have a 0 at 4. Looks good. So given that, that means that what we're trying to evaluate is the limit as x approaches infinity of 4x minus 16 over 5x plus 1. And this, like you could do controlling term analysis work, you could actually demo it by multiplying up and down by 1 over x. That's obviously a great way to do it. No matter what you do, you're going to get an answer of 4/5. So there's our stuff. We've got that last one done. And again, not as hard, but again, being able to engineer and write out the equation of a line really helps you. It just kind of makes it so that it becomes less weird looking and abstract with like f's and g's in there. But you at least have the equation of what's happening for that section. Okay, moving forward, the next question we're supposed to ask is we're supposed to find the value of c less than 0 such that the limit as x approaches c of g of x is equal to 2. Now, I think when I did the solutions, I did all values where g of x is equal to 2. But for this case, for this problem, I'm going to go ahead and just focus on the value of c less than 2. Let me point out, though, that if we were talking about c values greater than 0, there would be 2 such points. One of them would be x equals 2 itself, where there's a hole at 2, 2. The other one would correspond to the point right here on our graph. So just know that if all c, then we'd have to consider those other values. So x is approximately, in this case, it looks like 4.5. But there we go. Know that those are out there. For our case, though, we want to focus on that c value less than 0. And in fact, looking at our graph, we can see that that value is going to come on the far left branch of the function. And if memory serves, we already calculated out the equation there. That was 3x plus 9. So basically, for x less than -2, g of x equals 3x plus 9. So basically, it's an important first place to start. And notice that although we should consider the values in here, we can see none of them actually hit x equal or y equals 2. So we're not going to make that mistake. From here, next looking pieces in, we want to figure out what's happening at -2, and we can see that the function is nicely continuous there. Notice it's a nice continuous line between, well, negative infinity and -2. So basically, because of that continuity, we can just straight up calculate g of -2. It's going to be 3 times -2. Oh, just kidding. I lied. We're trying to make sure that this whole thing is equal to 2. We want the limit as x approaches c of g of x, thank you, to equal 2, which means that we want 3c plus 9 to equal 2 itself. I was going to say that last one wasn't going to give me a number that made any sense. So solving this around, we'll get 3c equals negative 7. We'll get c equals negative 7/3. So again, my written solutions, I did all values of c based on what we had. In this case, though, we were only interested in values that were negative, so we got just one, negative 7/3. And keep in mind, negative 7/3 is negative 2 1/3, and does that not look pretty reasonable for there? Yeah, it does. So I think we did everything correctly, and we're in great shape right there. Finally, we're on to our last question of this limits review. Even down here, I can see it's on the last page number. Yes, very happy. So, but again, couldn't leave you off without some sort of challenging function here, or piece to work here to finish off this limits review. In fact, this has one of those skills that sometimes people get really confused with. So I'm going to try to really conceptualize it here and make this work. So we're asked to evaluate the limit as x approaches 13 of g of x minus 11 squared over g of x plus 11. And now this can be a little intimidating right off the bat because our graph is 5 by 5, so we don't see 13 at all. And then there's all these 11s moving around, we've got something inside happening, so lots of weird stuff going on. What I'm going to start with is just a strategy I took when I actually did this problem, mostly because I was near the end, I was going to take it really carefully. I'm going to use the limit properties. So first, actually I'll do it up here. First, using the limit properties, we can break this into a quotient of two limits. This is the limit as x approaches 13 of g of x minus 11. And of course this would all be squared using the power property. And then likewise in the denominator, we can turn this into the limit as x approaches 13 of g of x plus what is the limit as x approaches 13 of 11, but since it's a constant, we just get 11. So basically, like, now we've got everything kind of simplified down. So we need to look at each of these pieces. I'm going to start with the one in the bottom part. And you know, I've used only one color today, I'll use a second color. So I'm going to start down here. So if we want to evaluate the limit as x approaches 13, first and foremost, we can't just go look at the graph and pick off the y value. We need to think about what's happening on g of x when x is over at 13. So to get there, specifically, as we said before, when x is greater than a particular value, there's a certain line that the behavior follows. So particularly here, when x is greater than 3, g of x is going to be the line described right over here. Now we did this earlier. I want to say it was equal to 4x minus 16. Quick check confirms that's correct. So we know this is 4x minus 16. So given that, if we want to evaluate the limit as x approaches 13 of g of x, it's just going to be using direct substitution. 4 times 13 minus 16. That's 52 minus 16, which is equal to 36. So this portion right here, we can see has to be 36. What that tells me is that in our denominator, here we'll go back up for just a second. In our denominator, we're going to get this whole thing is over 36 plus 11. And basically then we'll just need to evaluate that to finish this off. So that takes care of the numerator, or the denominator. Like, denominator wasn't too bad, we just had to figure out what the function's behavior was like when x was up there. Next though, let's look at the numerator. The numerator is definitely the toughest. And in fact, the hard part here is we need to evaluate the limit as x approaches 13 of g of x minus 11, which isn't even what we're looking at over there. So there's a couple ways to do this. In the problem set video solutions, one of the things I did is I did a full variable change to get there. That's one way to approach it. It's not necessarily the way I've always done it before, but it's one way. Here, I think if you're trying to work your way through this and you're confused by this, the best way is to think about what happens when you plug in x minus 11 to a function. So specifically, g of x minus 11, oops, I hope I did it right. G of x minus 11 is the graph of g of x shifted. That's all it is. Nothing's changing y value-wise. We're just moving around where they fall. So g of x minus 11 is g of x shifted 11 units to the right. So basically we're looking at something that's happening over here. So we just got to find the equivalent behavior spot. So now a couple things. So first, as x approaches 13, would you agree that g of x, or x minus 11 approaches 13 minus 11, which is 2? So basically, in a sense, what this is telling us is that in x minus 11 world, x minus 11, or sorry, x going to 13 is the same thing as describing x going to 2 normally. So basically what I'm going to do here is I'm going to make a translation. The limit as x approaches 13 of the shifted version of the function is equal to the limit as x approaches 2 of the unshifted function. What we've just accomplished is we've translated from being something here that's awkward and moved around to something that we can literally see on our graph. In fact, this has even come up a little bit in one of our earlier discussions. The limit as x approaches 2 of g of x is equal to 2. So given that, we were able to locate our value, and it was all about transformations, figuring out what that transformation does, and then evaluating the appropriate limit at the original graph. Having the value of 2, though, means that we can go finish this off. That limit is 2, and of course we're squaring it. Bringing it all full circle here, we'll get that our limit has value 4 over 47. And that completes the limit review. Now, obviously the difficulty here, there's some difficult problems in here. There are also some really easy ones. I think that this is a really good representation of the sorts of questions and the style of questioning and the depth of kind of questioning that could appear on the exam. Obviously, we're not going to have 24 massive questions like this on the exam. You'll have, some of these topics, all these topics will be addressed. Most of the question types in here will appear in some form, but obviously we won't be able to hit every single thing. And there may be a topic or two here or there that appear on there that aren't exactly represented here. But in any event, I hope that this extra assistance with the video or with the review, using the video solution process to get there, is helpful to you and helps you prepare for the exam. I know it's on short notice, but I think you guys are going to do great. And again, thanks for watching, and may this be helpful to you as you prepare for that exam. Have a good day.